Every few months, Bitcoin dies again.
Now, Bitcoin can sell to $100,000 a Bitcoin before it goes down.
Bitcoin is going to zero. Zero.
It's governments, it's energy use, it's Tether, it's China banning it. Maybe Satoshi comes back. But there's one threat that feels different, and this is a threat that Satoshi themselves flagged back in 2010. Quantum computing.
It will come to a bad ending, Charlie.
The predictions can be pretty terrifying.
Quantum computer is coming.
And honestly, a lot of these claims are plausible because quantum computers have a lot of unknowns about them. So today, I'm asking the question, what would have to be true for quantum computers to actually be a threat to Bitcoin? I'm Charlie Spears, this is Blockspace, and we're going to talk about quantum computers and Bitcoin. This is episode 1 in a multi-part series from us at Blockspace on quantum computers. This is a 101, a more beginner-friendly episode, so if you don't know anything, this is an explainer. There will be more episodes, and we'll talk to some of the experts to dive deeper into the subject. But before we go to Bitcoin, we have to zoom back and look at quantum computing itself. I think a lot of people, myself included, have this idea that quantum computers are like this glowing golden chandelier hanging down in a freezer, and that it's like way faster than anything, and that's not really true. Maybe that's kind of what quantum computers look like today in their prototype phase, but it's a little misleading. So you may already know that a regular computer uses bits, that's ones and zeros, that can be off and on. Quantum computers use qubits, Q-U-B-I-T-S. That can be 1 and 0 at the same time, kind of. So a classical bit is kind of like a coin lying on a table. It's either heads or tails. A qubit is like a coin that is spinning. It has some probability of being heads and some probability of landing on tails. That's its superposition. It's not necessarily both heads and tails at the same time, but rather it is undetermined until it's measured. This gets into entanglement and interference. When qubits are entangled, the state of one is correlated to the state of another qubit, regardless of distance. When you set up a computation correctly, you can get interference. That's where the wrong answers can cancel out and the right answers reinforce the correct answer. This is pretty important because quantum computers don't try all the answers at the same time. They have to be carefully orchestrated so that the probability of measuring the correct answer is high. It's less like trying all the answers at the same time and more like tuning a musical instrument so that it produces the correct frequency. Let me try saying it another way. A quantum algorithm uses this entanglement to create many computational paths simultaneously, and it then nudges them so that those paths leading to the right answers cancel out the paths leading to the wrong answers. It's like when waves meet. In fact, there's a lot of talk about waves. You're more like tuning the system so it produces the right answer instead of trying every answer really quickly. And this is what a lot of people miss about quantum computers. They aren't super fast computers. They're computers which help solve very specific types of problems. These problems that they solve are problems with a specific or particular mathematical structure that quantum interference can exploit. For most of your everyday computing, like watching YouTube videos, browsing, even like maybe probably AI compute, quantum computers don't really make those faster. In fact, they may be actually worse than regular computers. So when someone says quantum computers will break everything, that's not really true. Quantum computers probably won't break the things you normally do on your computer. They will break very specific things, maybe like encryption. Encryption is what keeps your Bitcoin yours, and encryption is the underpinning of all of the security on the internet.
We are CleanSpark, America's Bitcoin miner, a publicly traded company with the largest operating hash rate, powered entirely by self-operated infrastructure across 4 states. This is our proof of work, and we are setting the standard for what's next. Learn more about the intersection of energy and Bitcoin at cleanspark.com.
The year is 1994. A mathematician named Peter Shor publishes a paper that doesn't get much circulation outside of academia. That's because at the time, quantum computers didn't exist. But Shor proves that if quantum computers did exist, then they could probably break all the encryption that protects nearly all of digital communication. Modern encryption relies on mathematical operations that are easy in one direction and essentially impossible to reverse in the other direction. Multiply two prime numbers, you can find the answer instantly. But to figure out which two prime numbers are multiplied, especially large ones, that would take every computer on Earth working constantly longer than the sun will ever exist to find the answer. That asymmetry is the lock that secures your bank account, your messages, and your Bitcoin. But Shor found a way to pick the lock, and it really comes down to finding a pattern. Here's an analogy. Imagine you're looking at a tiny piece of wallpaper, just a few inches away. If you're close, it looks random, it could be anything, but if you zoom out and see the whole wall, you'd notice that pattern repeats. Every 18, 24 inches, same pattern. The repetition length, 18 or 24 inches, that is called the period. Numbers have something similar inside of them, like this wallpaper analogy. When you do certain operations over and over, for example, multiply, take the remainder, repeat, the results eventually cycle back to where they started. The length of that cycle is mathematically related to the factor of the number you're trying to crack. Classical computers can find this cycle, but they can only find it by computing each step one at a time, kind of like measuring that wallpaper inch by inch until you spot the repetition. For big numbers, there are more steps than there are atoms in the universe. Quantum computers are like looking at the entire wallpaper all at the same time. Using superposition, a quantum computer calculates all of the steps simultaneously. Then interference, that wave cancellation I mentioned earlier, filters out everything except for the period. Bitcoin uses elliptic curve cryptography on a curve called SEC P256K1. SEC P256K1. This is different than the RSA encryption that Shor originally targeted, but it's vulnerable in the same fundamental way. There is a cycle, or a period, you might say, hidden in the relationship between your private key and your public key. If you find this cycle, you find the key. The math is different than what I described earlier, but the principle is the same. A private key is really just a number. Your public key is that number, but transformed through elliptic curve cryptography. Quantum computers can reverse that transformation, not by guessing, but by seeing the hidden pattern that makes the reversal possible. So now we finally get to how Bitcoin uses cryptography, because that's what determines what Bitcoin is vulnerable. When you create a wallet, you generate a private key, a 256-bit random number. From that private key, you derive a public key using the elliptic curve cryptography. It's very easy, as I said, to go from private to public, and it's theoretically impossible to go from public to private. That is the asymmetry that Shor's algorithm breaks. But here's the thing, and this is a common misconception. Your Bitcoin address probably isn't your public key. It's a hash of your public key. Hashes are completely different, and Shor's algorithm can't touch them, can't reverse engineer them. So if you've only shared your address and never your public key, a quantum attacker can't work backwards because they don't have your public key to reverse engineer your private key. They'd have to break the hash first, which is a totally different problem. For the majority of Bitcoin's history, addresses have been hashes of public keys. The public key only gets exposed when you spend your Bitcoin, but there are exceptions. For example, the early Satoshi era coins from the 2010s. Also, ironically, taproot addresses, the newest address format, those are exposed when they're in flight, when they're unconfirmed. You can kind of think of your address like a PO box number. It's anonymous, Your public key is like showing your ID to prove that you own that PO box. Once you've shown your ID, someone with the right tools could theoretically figure out where you live. That's kind of like public-private key and hashes. And we know which Bitcoin is held in which address type. So we know which Bitcoins are the most vulnerable to reverse engineering via a quantum computer exploiting Shor's algorithm. So here's where quantum doesn't break Bitcoin, and that's Bitcoin mining. Mining is like a lottery. You just keep guessing numbers until you win. There's really no shortcut, and that's where quantum computers don't really apply. Quantum computers could theoretically guess faster using something called Grover's algorithm, but that's only a little bit faster. It's kind of like reducing a trillion-year problem down to a billion-year problem. So the signatures, the cryptography that secures your Bitcoin, that is what's vulnerable to quantum computers. So there's a specific pile of Bitcoin that makes this problem particularly more urgent. That's Satoshi Nakamoto's Bitcoin. In the early days of Bitcoin, 2009, 2010, Satoshi Nakamoto mined about 1 million Bitcoin. Today, those Bitcoin are worth tens of billions of dollars. Here's the problem. Those early coins exist in addresses where the address type actually reveals the public key. So those Bitcoin are just sitting there, exposed on chain. They've been visible for 15 years. A quantum attacker kind of sees that as a bounty. They're just available, waiting for the taking if a quantum attacker wants to exploit them. And beyond Satoshi's coins, estimates suggest about 2 to 4 million Bitcoin total are in similarly vulnerable situations. That's potentially 10 to 20% of all Bitcoin that's just sitting there, quantum vulnerable. So would draining all this Bitcoin kill Bitcoin? Well, that's actually quite the debate right now. Developers are surprisingly split. The market chaos absolutely would be severe, but what is too severe for Bitcoin? It's genuinely unclear and quite an ethical dilemma for the network, and the arguments are compelling on both sides. Some say freeze the vulnerable Bitcoin, Satoshi's Bitcoin, and similar types of OG Bitcoin before quantum arrives. Others say that freezing coins, even lost coins that we know nobody has, crosses an ethical line. Is it okay to burn or freeze Satoshi's fortune even if they're probably not coming back? Is it okay to freeze unknown OG Bitcoiners' Bitcoin? We see they do come back. These aren't hypotheticals anymore. We'll get into what freezing looks like, but we're actually having to talk about and argue about these responses to the quantum problem. We'll address this in later episodes. So how long do we have until a quantum computer steals Bitcoin? The honest answer is nobody knows, and this is a heated debate. Getting into it a little bit, here's some math and numbers. Breaking Bitcoin's cryptography requires roughly 2,000 to 4,000 logical qubits. But logical qubits aren't real physical qubits in the real world. That's just the math. Then we actually have to make the qubits physically. And you need more physical qubits than you need logical qubit. It's a whole thing. And then you have this whole issue of error correction and noise. As I said earlier, quantum computers have to deal with uncertainty and wrong answers. The whole problem right now is making qubits work together reliably, not giving you the wrong answer and giving you the right answers. A lot of critics say that this is an intractable or unsolvable problem. It is theoretically impossible. So where are we today? Things are moving fast, and it's difficult to discern where we actually are. IBM says they have 1,000 physical qubits. Google's Willow chip says 105. But we need 4 to 5 magnitudes more qubits. And this really isn't a predictable curve. Like, is this something that happens in 10 years, 40 years? A lot of people do accept that quantum computers are probably going to happen in some form eventually, but this really is a timeline question. How urgent is this? NIST, the National Institute of Standards and Technology, the US agency that sets cryptographic standards for the federal government, effectively like the world, finalized post-quantum cryptography standards in 2024, so fairly recently. So when NIST moves on something like this, it indicates the intelligence community also sees a credible threat. Like, surely they're not preparing for nothing. Bitcoin does have some time, but not infinite time. And the question is this a 2 to 3 year problem, a 5-year problem, or a 50-year problem? So where do we stand? Is there a solution? Is there even a problem? Well, that's currently being discussed. My personal evaluation is that this is the most heated this discussion has ever been, and it's notable because it heated up a lot recently. There have been significant advances in quantum computing research, and a lot of the foremost researchers are kind of saying it might be closer than we thought. The good news is that post-quantum cryptography exists, stuff that Shor's algorithm wouldn't break. There are new signature schemes believed to resist classical and quantum attacks. And NIST, as I mentioned earlier, has finalized some standards. In principle, Bitcoin could adopt one of these post-quantum resistant schemes and safeguard itself and its users against a quantum attacker. You'd have to introduce a new address type, and it would come with additional changes beyond that that could also be controversial, such as block size. And users would also have to migrate their funds, presumably. This is not a new conversation by any means. Quantum discussions in Bitcoin developer circles go back since the genesis of Bitcoin. But now we're actually starting to see drafts of real solutions to this risk, and we're seeing developers debate these solutions. There are draft BIPs, Bitcoin Improvement Proposals, the conventional way of introducing changes to Bitcoin through forks, either soft fork or hard fork, and these explore various approaches. But in my opinion, the real problem is not necessarily a technical one, but rather a coordination one. How do you figure out if everyone agrees that there is a correct solution, and then you have to go execute that solution? Bitcoin changes slowly. Can it change fast enough for quantum? Does it not have to change quickly? Does it ever have to change? These are still being debated. For example, the most recent upgrade, 2022 Taproot, that was years of discovery and research, and it was relatively uncontroversial. Post-quantum migration could be the most complex because it involves multiple dimensions of Bitcoin. Do we freeze or not freeze? How do we migrate? What specific signature scheme is reliable? Do we feel comfortable with that? Has the CIA put a backdoor in this signature scheme? You know, this is stuff that we're baking into Bitcoin for years, forever, really. And you have to be very careful and cautious. My read, cards on the table. I don't think anything will happen in 2026. It's January now. This is just an early discussion. I also don't think it'll be a problem that nothing happens in 2026, at least as far as quantum. But there are more questions than answers, and I don't say that lightly as kind of some hook. It actually is a very confusing topic, and a lot of the people who specialize on this, quantum researchers, quantum professors, so the leading quantum professors are constantly asking new questions that they themselves don't know the answer to. We are going to explore this topic. I have some experts in the Bitcoin industry lined up talking about it over the next few episodes. If you like this, make sure to like and subscribe to this feed, Blockspace Podcast. We're going to be doing more content like this, especially quantum, over the coming weeks. Make sure you stay tuned.